10,000 billion billion. Write that number out. It has 22 zeros. That is how many molecules of air just went into your lungs in the breath you took about 3 seconds ago. Take another breath. There goes 10,000 billion billion more. Your body has been doing this every few seconds since the moment you were born. It does not stop when you sleep. It does not stop when you forget about it. And it won't stop while you listen to me. Now I want you to do something. Pick one of those molecules. Any one. It does not matter which. There's one hovering a few inches in front of your face right now, about to enter your body. Just pick it. I'll wait. Got one? Good. Here is what nobody tells you about that molecule. It is older than the sun, not by a little, not by a few million years, by a great deal more than that. Some pieces of that molecule were cooking in the furnace of a dying star when our sun was not even a rumor in the interstellar medium. Some pieces of that molecule existed when the entire universe was less than a half hour old. And I can prove it to you. You should be suspicious. You ought to be. This is the kind of claim that sounds like a professor showing off, and when a professor starts showing off, you should check his arithmetic. So we are going to do something today that physicists love to do when we want to understand a thing all the way down. We are going to zoom. We are going to start in this room, with this breath, with this one molecule. And we are going to keep zooming, in and out, until we arrive at the answer. You'll know when we get there. You will not be able to forget it. Here we go. First zoom. The room itself. Look around wherever you happen to be. The air in this space feels like nothing to you. You cannot see it. You do not really weigh it. It does not get in your way. You walk through it 1,000 times a day and never notice you are walking through anything at all. But the air is a substance, a real, physical, weighable substance. All the air in an ordinary living room weighs somewhere between 40 and 100 pounds, depending on how big the room is. If I could reach over and suddenly remove it, you would hear a noise that would rupture your eardrums, and your skin would bruise from the pressure of the air above the room, crashing down to fill the gap. You are swimming in a fluid that pushes on every square inch of you with about 15 pounds of force. You've always been swimming in it. You just can't feel the water because you are the fish. This air is made of molecules, little bundles of atoms bound together by electrical forces. Most of what is rushing into your face right now is nitrogen, bound up in pairs, 2 atoms stuck together like a little dumbbell. About 78% of every breath is nitrogen. Another 21% is oxygen, also in pairs. The remaining 1% is mostly argon, which floats around alone, refusing to bond with anyone, very snooty and aristocratic about the whole thing. There are trace amounts of water vapor, carbon dioxide, neon, helium, methane, and a whole cast of bit players in quantities so small you could ignore them if you were not a careful person. Here is a thing most people never sit with. The molecules in the air are not still. They are moving fast, extremely fast. At ordinary room temperature, a typical nitrogen molecule is zipping around at about 1,500 feet per second. That is faster than most rifle bullets. The air in this room is a storm of bullets, slamming into each other and into you billions of times every second. You don't feel it because the bullets are too small to do individual damage, and they hit you from all directions at once, so they cancel out, and you just feel a gentle pressure and maybe a draft. But don't let the stillness of the room fool you. The air is a riot. It is a screaming, chaotic, kinetic riot, and somewhere in that riot is the molecule you picked a minute ago. Hold on to it. Second zoom. In closer. Let us shrink down and look inside one molecule of oxygen. It has 2 atoms stuck together. Take one of them. Take one atom. Now, if you could peek inside that atom, you would find a tiny dense core in the middle called the nucleus, and a cloud of electrons buzzing around it. I want to give you a sense of the scale here, because people always say atoms are mostly empty space, and they never quite convey how much empty space we are talking about. If you blew up an oxygen atom until the nucleus was the size of a green pea sitting on the table in front of you, the nearest electron would be about 2 football fields away. 2 football fields. All the rest is empty. You, as solid-looking as you are almost entirely nothing at all. When you clap your hands together, you are not slapping matter against matter. You are pushing one cloud of electrical repulsion against another cloud of electrical repulsion. The sound you hear is the universe refusing to let your hands occupy the same place. But that tiny pea in the middle of the atom, the nucleus, that is where the interesting stuff lives. The nucleus is made of protons and neutrons jammed together. The number of protons is what determines what kind of atom it is. 8 protons, it's oxygen. 7 protons, it's nitrogen. 6 protons, carbon. 18 protons, argon. 1 proton, hydrogen, the simplest atom of all, just one little pea with a cloud around it. Now I am going to ask you a question. And I warn you, once you ask this question, there is no going back. It is the kind of question that cracks a whole subject open. The question is this: where did those protons come from? Not the molecule, not the atom, the protons. The tiny things at the very heart of the matter. Somebody had to make them. They don't just appear. They don't fall out of the sky. They had to be manufactured somewhere by some process. Who made the protons in the nitrogen in your lungs? Who made the protons in the oxygen in your blood? This is the question. Once you have it in your head, you cannot get rid of it. Everything in physics hinges on it. Third zoom. Way out. The universe itself. I am going to take you as far out as we can go. Past the Earth, past the moon, past the sun, past the planets, past our whole galaxy, past the nearby galaxies, out to the biggest scale we have any hope of seeing. And I am going to take you back in time. The universe, as best we can tell, has a beginning. This is not a religious claim. It is a measurable one. When you look at the light coming from distant galaxies, you find that every galaxy is rushing away from us. And the farther away a galaxy is, the faster it moves. Now, if you run the motion picture of that backwards, everything rushes together. Keep running it backwards, and you eventually reach a moment when all the stuff in the universe was crushed together into an unimaginably small region, unimaginably hot, unimaginably dense. That moment was about 13.8 billion years ago. We call it the Big Bang, which is a silly name because it was not really a bang and there was no sound, because there was nothing outside the universe for the sound to bang into. But the name stuck, and now we have to live with it. What happened in that early universe is that everything was incredibly hot and began to expand and cool. The first seconds were wild. There were no atoms yet. There were not even protons and neutrons as stable things. There was just a broth of the most fundamental particles, too hot and too energetic to stick together into anything complicated. Then, as the universe expanded over the first 3 minutes, the broth cooled down enough that protons and neutrons formed, and some of them started bonding. Hydrogen nuclei appeared, which is easy, because a hydrogen nucleus is just one proton all by itself. And then some of those hydrogens fused into helium. A little bit of deuterium formed, that's hydrogen with an extra neutron, a tiny amount of lithium. And then, just as the nuclear furnace was getting interesting, the universe expanded and cooled too much to keep it running. The door slammed shut. The fusion stopped. By the end of the first 20 minutes of the universe, the cosmos was a cloud of roughly 3/4 hydrogen and 1/4 helium, with trace amounts of a few lighter things. That was it. No oxygen, no nitrogen, no carbon, no iron, no copper, no gold. None of the elements that make up your body, your chair, your house, your dinner. The early universe was incredibly, almost insultingly, simple. 2 ingredients, basically, and if you wanted to study the chemistry of the whole universe at that time, you could fit it onto one small note card. Now I want you to stop and look at your hand. Your hand is made of carbon. Billions of carbon atoms in every cell. It is also made of oxygen, nitrogen, calcium, phosphorus, iron, and a dozen other elements. Your hand is enormously complicated. It has intricate chemistry going on in it every second, and it is possible only because of the richness of the periodic table. The early universe was not rich. It was thin, simple, almost empty of interesting possibilities. So somewhere between that thin, simple beginning and today, somebody built all these heavier atoms. Somebody took plain hydrogen and stacked it, by ones and twos and threes, into everything else. Who? Fourth zoom. Back inward, all the way inward, into the heart of a star. A star is a place where gravity has crushed a cloud of gas so tightly that the pressure and temperature at the center become unbelievable. At those pressures, in that heat, protons can be forced so close to each other that they overcome their mutual repulsion and fuse. Hydrogen goes in, helium comes out, and a little bit of energy is released in the process. That energy pushes outward, balances the inward pull of gravity, and the star shines. Our sun is doing this right now. It has been doing it for about 4.5 billion years, and it will keep doing it for another 5 billion or so. It is a great, luminous thermonuclear furnace, fusing hydrogen into helium at a rate of roughly 600 million tons per second. That is an almost meaningless number to the human mind. I cannot really picture it, neither can you. But the sun does it, and it will keep doing it for a long time, and that is why the earth is warm. Here is the first big thing I need you to see. Hydrogen into helium fusion only gets you helium. It does not get you oxygen. It does not get you nitrogen. It does not get you carbon. For those you need a bigger star, a hotter core, and more time. In the biggest stars, after the hydrogen in the core runs out, gravity pulls the core tighter. It gets hotter. And suddenly helium itself can fuse. 3 helium nuclei slam together almost simultaneously, and the result is a carbon nucleus, 6 protons and 6 neutrons. This is called the triple alpha process, and it is a small miracle of timing, because 2 helium nuclei on their own can't stick together stably. You need a third one to come along at just the right moment, and the universe had to be set up with very precise physical constants to make this work. If the constants were even a little different, there would be no carbon in the universe at all. No life, just hydrogen and helium, forever. But we got lucky. The numbers are what they are. Carbon gets made. And it goes on. Once you have carbon, you can fuse a helium onto it, and you get oxygen, 8 protons. Now you have the oxygen you are breathing right this moment. Stack another helium on, you get neon. Another, magnesium. Another, silicon. In the heart of a massive dying star, you have a thing that looks like a cosmic onion. The outer layers are still burning hydrogen. Below that, a shell of burning helium. Below that, carbon. Below that, oxygen. Below that, silicon. Deeper and deeper, heavier and heavier elements, all the way down to a core of iron. At iron, the whole process stops cold. Iron is the most tightly bound nucleus that exists. You cannot squeeze energy out of fusing iron into anything. When the core of a massive star turns to iron, the star is out of fuel. And what happens then is one of the most violent events in the universe. The core collapses. In less than a second, a ball of iron the size of the Earth implodes down to something roughly the size of a small city. When it hits bottom, it rebounds, and the shock wave tears through the rest of the star. The whole star explodes outward. We call it a supernova. For a few weeks afterward, a single exploding star can outshine a whole galaxy of 100 billion other stars. And every element that star had been cooking in its onion layers gets blown across the cosmos. Carbon, oxygen, nitrogen, silicon, sulfur, iron, everything up to and including some of the heavier metals that get made in the explosion itself. A supernova is a factory and a delivery service rolled into one. It makes the heavy stuff, and then it flings it out into space for anybody to use who comes along later. This is how the universe got complicated, not all at once. Not in the first 20 minutes. Slowly. Over generations of stars being born, living, dying, and salting the cosmos with heavier and heavier elements. Every atom in your hand heavier than hydrogen was, at some point, inside a star. That is not a metaphor. That is the history of the material. Fifth zoom. Now the numbers start to sing. Our sun formed about 4.5 billion years ago. We can state that with great confidence, because we have measured it. The oldest rocks in the solar system, a particular kind of inclusion found in certain meteorites called calcium-aluminum inclusions, contain radioactive elements whose decay tells us exactly when they first became solid. The answer is 4.5 billion, give or take a few million years. That is when matter in our little corner of the galaxy began sticking together into solid objects. That is when the solar system was born. But the universe itself is 13.8 billion years old. Subtract one from the other, 9 billion years. 9 billion years between the beginning of everything and the birth of our sun. 9 billion years during which stars were forming, burning, running out of fuel, dying, scattering their guts across interstellar space, and the guts of those stars drifting together in clouds, forming new stars, and the new stars dying too, and on and on. Our sun is not a first-generation star. It is not a second-generation star. It is a third-generation star at the very least, probably a descendant of many previous generations of stellar births and deaths. And all of those earlier stars, every single one of them, was busy making atoms. Oxygen atoms, nitrogen atoms, carbon atoms, the atoms in the air you are breathing right now. Let me say this more plainly, because I want it to sit inside your head. The oxygen in the air did not come from our sun. The sun does not make oxygen. The sun is still in the hydrogen-burning phase of its life. For the sun to start making oxygen, it would have to be much more massive than it is, or it would have to reach a much later stage of its life, billions of years from now. The sun will never, in its entire lifetime, produce a meaningful amount of the atoms you are breathing. So where did they come from? They came from earlier stars. Stars that lived and died before our sun was born. Stars that fused hydrogen into helium, into carbon, into oxygen, into nitrogen, and then exploded and scattered those atoms across interstellar space. The debris of those stars drifted through the galaxy for hundreds of millions of years, sometimes billions. It mixed into giant clouds of gas. Those clouds, already seasoned with the ashes of dead stars, eventually collapsed under their own gravity to form new stars and new planets. About 4.5 billion years ago, one such cloud collapsed and formed our sun, and all the leftover crumbs clumped together into the planets. Earth is a crumb, a wet, warm, interesting crumb. And every atom in Earth, except for hydrogen and helium and a pinch of lithium, was already old when the sun ignited. The atoms in the air in this room are older than the sun. Most of them, considerably older. A typical oxygen atom in your lungs was forged in a star that died perhaps 5, 6, 7 billion years ago, maybe more. The hydrogen bound up in the water vapor in your breath is older still. The hydrogen atoms formed in the first 20 minutes of the universe. 13.8 billion years old. More than 3 times the age of our sun. Think about what this means for your body. When you drink a glass of water, every hydrogen atom and every water molecule in that glass is older than our star, older than the Earth, older than our galaxy and anything like its present form. You are mostly water. The water is ancient. You are drinking the dawn of time, slightly reheated. Sixth zoom, a fair demand from a careful listener. Now, if you are sensible, you are not just nodding along. You are saying, all right, you've told me a pretty story. Where is the proof? How does anyone know this actually happened? Maybe it's guesses dressed up in numbers. That is the right question to ask, and if you were not asking it, I would be worried about you. So let me show you what we actually have. We know the age of the sun because we can measure it from rocks. Certain meteorites preserve the very first condensed material of the solar system. Those white blobs inside them, the calcium-aluminum inclusions, contain isotopes of uranium and lead whose radioactive decay acts like a clock. You measure the ratios, you read the clock, you get 4.5 billion years repeatedly from different samples in different laboratories by different people. The number is solid. We know the age of the universe from several independent measurements. One is the rate of expansion, run backwards. Another is the light left over from the early hot universe, a faint microwave glow that fills the sky in every direction, which matches the predictions of hot Big Bang cosmology with astonishing precision. Another is the ages of the oldest stars we can find, which are almost, but not quite, as old as the universe itself. All these numbers agree. 13.8 billion years. The universe is that old, and we know that nuclear fusion in stars actually produces the heavy elements, because we can see it. We have watched stars. We know their spectra. Young stars have fewer heavy elements than old stars, on average, because they formed out of clouds that had not been enriched by many previous generations of stellar death. Stars very near the middle of our galaxy tend to be more metal-rich, because more generations of stars have lived and died there. The pattern holds up everywhere we look. The galaxy is running a chemistry experiment, and we can see the progress of the experiment by reading the starlight. But here is my favorite piece of evidence. And I am going to linger on this one because it blows my mind every time I think about it. Inside some of those ancient meteorites, embedded in the matrix like little raisins stuck in a loaf of bread, there are microscopic grains of dust. Grains you can only see with powerful microscopes. And these grains have isotopic compositions that are wildly, impossibly different from the rest of the solar system. They do not match our sun. They do not match our Earth. They look like material that formed around completely different stars, with different nuclear histories, with different mass ratios. These are called Presolar grains, literally before the sun grains. They are tiny bits of dust that were blown out of dying stars somewhere else in the galaxy, traveled through interstellar space for probably hundreds of millions of years or more, and then got caught up in the cloud of gas that collapsed to form our solar system. When the sun ignited, these grains were already there, already old, just floating in the soup. They survived the whole process of solar system formation, got incorporated into asteroids, and eventually fell to Earth as meteorites. We have them. In laboratories. Right now. People hold them. They photograph them. They measure their isotopes to see exactly which kind of star they came from. Some of them came from red giants. Some from supernovae of different types. Some from stars we will never see in their original form, because those stars are long dead. A piece of a star that died before our star was born. Sitting in a jar on a shelf. Think about that for a little while. Now the atoms floating loose in your air don't have individual tags saying which star they came from. They've been mixed up and shuffled too thoroughly for that. But the rocks have the signatures, and the rocks agree with the physics, and the physics agrees with the ages of the stars, and the whole thing hangs together as one consistent story. The atoms in your breath are older than our star. That is not a hopeful speculation. That is the verdict of the evidence, reached through many different windows, by many different people with many different methods, and they all give the same answer. Seventh zoom. A little honesty about the tricky cases. I have to be careful here. A really careful listener might push back. They might say, "Hold on, you said all the atoms in the air are older than the sun, but some things in the air are young. Water vapor might be formed yesterday, carbon dioxide a plant just exhaled. Some argon on Earth, I seem to recall, is actually made by radioactive decay inside Earth's rocks. Are you being sloppy? No, but the listener is right to press. Let me be more careful. When we say the air is older than the sun, what we mean is that the atoms in the air are older than the sun, not that the molecules are. A water molecule might have been assembled this afternoon, when a pair of hydrogen atoms joined an oxygen atom to make water. The molecule is young, possibly only hours old. But the atoms inside it are ancient. The hydrogens go back to the Big Bang. The oxygen was born in some long-dead star. A molecule is like a sentence. The sentence might be brand new, but the letters that spell the sentence are old. We keep reusing them, pulling them apart, putting them back together into new words and phrases. We do the same thing with atoms. Atoms are the true alphabet of the physical world. They outlast their arrangements by many billions of years. And yes, there is a specific case that is worth mentioning. A particular kind of argon in the atmosphere, argon-40, is mostly not left over from the solar nebula. It is made inside the Earth. Potassium-40, which sits in rocks, slowly decays over billions of years and turns into argon-40, which leaks up through the crust and adds itself to the atmosphere. So when you breathe in argon, some of those argon atoms are relatively young. They were made inside the Earth well after the Sun formed. But here is the twist. Those argon atoms are made of protons and neutrons that were themselves in the potassium-40 before the decay. The potassium was made in a star long before our Sun existed. So the building blocks of the young argon are ancient. The atom has been rearranged, but the nuclear material was forged in some presolar stellar furnace. If you follow the protons all the way back, the history still goes through a dying star older than our Sun. Atoms do not lie about their age, but you have to know how to read their family tree. 8th zoom. Back to you. Back to the breath. I want to give you a sense of the numbers one more time, because I think they are the best numbers in physics, and they make people feel things. In the breath you just took, there are 10,000 billion molecules. 22 zeros. The Earth's atmosphere contains about 100,000 billion molecules total. A whole lot more zeros. If you work out the ratio between one breath and the whole atmosphere, you find that a single breath is about 1 molecule per breath-sized parcel of air on the entire planet. This leads to a remarkable little game. If you assume, and this is a reasonable assumption, that the atmosphere has had time to mix thoroughly over hundreds or thousands of years, then every breath you take, statistically, contains at least 1 molecule that was in the dying breath of Julius Caesar, and Socrates, and Cleopatra, and your own great-grandmother. Every breath ever exhaled by every human who ever lived has scattered into the atmosphere, and some of those molecules, by sheer probability, end up coming back to you. But forget Caesar. Go further back. Every breath contains molecules that passed through the lungs of cavemen and woolly mammoths, through the gills of ancient fish on prehistoric beaches, through the leaves of the early forests, through the great tree ferns, through the pores of single-celled creatures floating in a younger ocean. The air is a circulating library, and we keep checking out the same volumes and returning them to the shelves. Every breath you take was in many other breaths, many other lungs, many other lives, before it got to you. And all of that history is just what happened on Earth. The atoms themselves were already ancient before Earth existed. A single nitrogen atom in your breath might have been cooking inside the core of a red giant 8 billion years ago. It might have been ejected in a gentle puff of stellar wind, as that giant turned into a planetary nebula and shed its outer layers. It might have drifted through interstellar space, cold and alone, for 1 billion years. It might have been swept into the cloud that became the solar system. It might have been incorporated into the primordial atmosphere of Earth, into the early oceans, into the first microbes, into the proteins of every creature that has ever lived. And right now it is inside you, and in about 3 seconds you are going to exhale it. And it will begin the next leg of a journey that will probably go on for many more billions of years, long after you and I and everyone we have ever heard of are dust. You are a temporary meeting point for very old atoms. They pass through you. You are a waypoint on their incomprehensibly long trip through the universe. 9th zoom, the oldest stuff of all. Let me come back one more time to that hydrogen. The oldest stuff in you. The oldest stuff in your breath. The hydrogen atoms bound up in water vapor, in methane, in trace molecules scattered through the air. Those hydrogen atoms formed when the universe was about 20 minutes old. I want you to sit with that. 20 minutes after the beginning of everything, Nuclear reactions in the hot early universe produced the protons that became hydrogen atoms. And some of those exact same protons are, at this very moment, part of molecules that just entered your lungs. They have had almost the entire history of the universe to do what they have done. And what they have done is, eventually, become you for a little while. The hydrogen atoms in your body, almost all of them, are as old as the universe minus 20 minutes. You are a walking fossil of the early cosmos. Every time you drink a glass of water, you swallow bits of the dawn of time. Nothing in physics required this to be true. You can imagine a different kind of universe, one where atoms were constantly being created and destroyed, where the matter in your body was made just last Tuesday. We do not live in that universe. In our universe, once a hydrogen atom is made, it tends to stick around. It is stable. Nothing destroys it unless a star gobbles it up and fuses it into something heavier. So the vast majority of the hydrogen that was ever made, some 13.8 billion years ago, is still out there, still hydrogen, still drifting, occasionally getting swept into planets, oceans, bodies, breaths. I think this is one of the most beautiful discoveries of physics. At first it sounds small. Who cares if the air is old? But when you sit with it, when you really let it into your head, there is something profound there. We are, each of us, assembled out of atoms with histories longer than anything the human mind can properly imagine. Every breath connects you to the death of stars. Every drink of water connects you to the first minutes after the universe began. You are a very recent arrangement of very old things. And you will come apart, someday, and those atoms will go on, nearly unchanged, into whatever comes next. The nitrogen in your lungs will drift back into the air, be taken up by plants, breathed by animals, blown across continents. The hydrogen will probably still be around when our sun swells into a red giant 5 billion years from now and swallows the inner planets. Even then, a lot of the hydrogen will be blown out into space, back into the wide galaxy, to drift, and maybe be caught up someday in some future star, some future world, maybe even some future living thing. Atoms get recycled through cosmic history. That is what they do. Atoms have deep time. We do not. But for a little while, we get to borrow them. That is what we are. Borrowers of ancient material, lent to us for a few decades, returned on our behalf, endlessly reusable. 10th zoom, the last one, right back where we started. Take a breath, just one. Do not try to make it special, just breathe. You have just pulled 10,000 billion molecules into your chest. Almost all of them contain atoms older than the sun. A great many of them contain hydrogen older than stars, older than galaxies, older than almost anything that exists. All of that cosmic history, all of that travel across billions of years, all of those furnaces and explosions and cold, silent drifts through empty space, and where does it end up? Right here, right now. Passing through your body, doing chemistry in your blood, coming back out of your nose, and being replaced immediately by the next breath, which carries the same ancient cargo. This is what it means to live inside the universe rather than somehow apart from it. You are not separate. You never were. You are a particular pattern, a very temporary one, woven out of extremely old threads, held together by electrical forces and chemical reactions and the strange, quiet insistence of physics. The pattern is brief. The threads are not. You got to be the pattern for a little while. So did I. That is the arrangement we have with the universe. Most of the time, there is not much you can do with this knowledge. You breathe. You go on about your day. You do not think about the atoms in your lungs while you wait for the water to boil or walk out to the mailbox. That is fine. You cannot live every minute in awe of the cosmic machinery. But once in a while, when you have a moment, preferably during a sunset or a thunderstorm or when the house is quiet and nobody needs anything from you, I would like you to stop. Take a breath. And remember where it came from. The atoms came from unimaginable violence, from the detonations of dying giants, from the first minutes of time itself. And now they are here. Now they are you. And now, just for a little while, they get to walk around and think and love and wonder, and perhaps listen to a lecture about where they came from. That is not a small thing. That might be the whole business of the universe, folded down into a single breath. I'd like you to do one last thing before you go. Take the deepest breath you can manage. Hold it for a moment. And while you hold it, think about this. Every one of those atoms passing through your body right now was forged in a place you have never been, in a furnace older than the star that gave us light. They have been in the lungs of every human who has ever lived, and the bodies of creatures we will never see. They have drifted across distances too vast to really picture. And in 3 seconds you are going to exhale them, and they are going to keep going, without you, into whatever comes next. Now tell me, when you exhale, where do you think those atoms are going? What do they become next? I would like to hear your best guess. Send it to me. I read them.